Every single day, 800 million vehicles burn through nearly 2 billion gallons of fuel. At the gas station pump, it feels like a simple liquid, but this flammable substance reaches the nozzle only after traveling through a high-pressure manufacturing process that begins miles underground. The modern petroleum industry was born in 1859, when Colonel Edwin Drake drilled the first commercial oil well in Pennsylvania. This discovery proved that liquid crude could be extracted at scale, sparking a global hunt for buried hydrocarbons. The demand for this crude accelerated in 1908, when Henry Ford's Model T made automobiles accessible to the average person. This technological shift moved internal combustion engines from a luxury to a necessity, locking the global economy into a permanent need for gasoline. During both World Wars, oil became a critical military resource. The ability to fuel massive formations of tanks, warships, and aircraft became a deciding factor in global conflicts, solidifying petroleum's role as a strategically vital asset. In just a few decades, these shifts integrated oil into almost every facet of life, from personal transportation to global military supply chains. This created a massive vacuum, a global society that now requires astronomical quantities of an explosive fluid just to function. This diagram illustrates seismic surveying, a process that acts like an MRI for the planet. Engineers blast powerful sound waves into the ground, which bounce back off subterranean rock layers. Sensors on the surface catch these signals and translate them into 3D maps to locate oil trapped inside porous rock. Reaching that oil requires drilling through sandstone, shale, and ancient granite. To do this, crews bolt together 33-foot sections of steel drill pipe. Depending on the rock's density, it can take an hour just to cut through a single section, with the process repeating hundreds of times until the well reaches its target depth. High pressure is the primary risk during drilling. If underground fluids escape in an uncontrolled rush, it triggers a blowout like the one seen here. To prevent this, engineers continuously circulate a heavy drilling mud to maintain pressure in the well and cool the drill bit. Once the initial underground pressure of a well dissipates, mechanical extraction takes over. Large pump jacks are installed to create subterranean suction, drawing the crude to the surface with a back-and-forth motion. Before leaving the site, the raw crude enters separation vessels. They strip out associated gases like natural gas and highly toxic hydrogen sulfide, leaving behind the stable crude oil required for refining. Extracting crude oil is a high-stakes battle against catastrophic geological forces. Once the raw material is secured and stripped of hazardous gases, it moves through pipelines toward the massive industrial complexes that handle the next stage. These refineries are staggering in scale, often covering thousands of square miles and processing 600,000 barrels of crude every day. It is here that raw earth is converted into specific consumer fuels through intense heat. The mechanical heart of the refinery is the distillation tower, shown in this diagram. Raw crude is superheated to 700 degrees Fahrenheit, causing it to enter the base of the tower as a high-pressure vapor. As the vapor rises, it cools. The heaviest molecules condense immediately at the hottest, lowest layer of the tower, dropping out to become asphalt and heavy fuel oil. Different molecules condense at specific heights based on their weight and the decreasing temperature. As the vapor moves up the tower, diesel condenses first, followed by jet fuel, and then kerosene. At the very top of the column, where temperatures are at their lowest, the lightest molecules finally condense. This top-tier liquid is the raw gasoline. A standard barrel of crude oil yields roughly 19 gallons of gasoline, alongside 10 gallons of diesel and 5.5 gallons of jet fuel. This process involves dismantling the chemical bonds of ancient hydrocarbons with extreme heat and pressure, then cooling them to reconstruct the specific fuels that power modern transportation. Every batch is tested in a combustion engine to verify its octane rating. This number represents the fuel's resistance to knocking, a condition where the gas ignites too early inside the cylinder and can destroy the engine. Moving this finished product is remarkably hazardous. As a tanker truck is loaded, liquid friction creates static electricity. Near gasoline vapor, a single spark like this one triggers a massive explosion. To prevent disasters on the highway, tanker trucks use grounding cables to discharge static buildup and vapor recovery lines to capture flammable fumes. These dual defense mechanisms ensure the fuel remains stable while traveling to its final destination. Transporting fuel is a daily, invisible logistics operation. It requires managing immense potential energy while neutralizing the constant threat of a single stray spark. At the gas station, the tanker truck locks its hoses onto the storage tank inlets. Gravity pulls the fuel silently into the underground tanks,
completing a journey that began miles below the Earth's surface. The fuel in the nozzle has already crossed hundreds of miles and survived extreme thermal and chemical pressures. It represents a long chain of fire, pressure, and testing that happens before you ever squeeze the handle. A single gallon of fuel is the end product of massive engineering risks, from the deep earth pressures of the oil field to the thermal precision of the refinery. It is a dangerous, silent logistics chain that remains largely invisible to the public. If you want to see more behind-the-scenes looks at the systems that power our world, drop a like and leave a comment telling us where you're watching from. Subscribe and turn on notifications for The Explainer so you never miss a new episode.